morning. Here we are once again. It is the physics video lecture. Physics 105B, video lecture 41. So we're talking about fluid mechanics, but actually I'm going to start off with some announcements while I have your attention regarding the rest of the semester. So let me write down what we have here. Remaining hours, we have today and Friday, and then next week, and that would be the last lecture of the semester, and then we'll have our final exam on the 14th. That's 8 to 10 or something like that, or 9 to 11. We'll have to look it up. So that'll be the standard format. Take the exam, mail it in, email it. So in order to be prepared for that, I actually want to take both of these hours next week to do major review on what's going to be on the final. That'll help us out. So that only leaves us these 2 hours to talk about fluid mechanics. And we'll cover something, and we've already tied together some really interesting material that we needed for Hamiltonian mechanics, so that's good. We'll make a little more progress in this direction. So that's the first point to be discussed. Let me know if you guys have any questions. In here, I'll return some homework, and then we'll have that final. So yeah, we just have these 4 hours, including this one right now. The second thing is that I'm going to offer a 1-unit 190 class next semester. So let me write this for spring 21. 1 unit, and we did this very successfully this semester with the complex variables discussion. And complex analysis was something I wanted to touch on in 105A, and we didn't get there, and yet we were able to do a much better job actually with that 1 unit class. So I'd like to do the same thing, 1 unit of 190, you know, a third of a semester, and that would be fluid mechanics. Now the situation here is that I actually have a full semester fluid mechanics course set up, but I only want to teach that when we're all back together again. But this could actually be pretty nice. So I'll send out an email discussing that a little bit more. 1 unit fluid mechanics, basically what we did last time, what we're going to do now, and then we carry it on into some other interesting material. The 3 unit class that I have in a year or so, or a year and a half, whenever, could then be expanded to fluid mechanics and elasticity theory. But my ambition for this one is to cover stuff that ties into the mechanics that we've done and make it a whole. Okay, so we would actually want to also make it to waves and fluids and things like that, wave equation. You may remember this semester we had the wave on a 1-dimensional chain. Right? We derived the wave equation, so we certainly need to do that in a fluid as well. But we're not going to get to that in these 2 days because that's a bit downstream. Downstream, no pun intended. But anyway, so this 1 unit class, and I would, I'll have to pull out the interesting and important stuff. I had noticed when I taught the fluids, I've done the whole 1 semester version before, and most of my students, upper division physics majors, really didn't remember anything from what they would have had in physics 4A. So one thing we could cover is to make sure we know everything that you're supposed to know from physics 4A in that chapter, but it gets much more interesting and technical what we're doing right now. Anyway, enough about that. So this is something we'll want to think about. I'll send an email out and see if we can drum up some interest for that. Some really nice material. Okay, so now we're back into where we left off. And I'll briefly recapitulate. So when we're doing fluid mechanics, it's a field theory because we have in our three-dimensional space a vector field that represents the velocity of the fluid at that point in space and as a function of time. So that's the velocity field. And then we also have the density also, but it's a scalar. And we've ended, with these two, we had the equation of continuity. So we had d rho dt plus divergence rho v equals 0 continuity equation. And that's the first important differential equation of fluid mechanics, and it's one equation because it's a scalar. Next, we started talking about force and pressure, and I did a little diversion over to hydraulics and stuff just to look at the basic concepts. But now we're going to look at the differential equation that deals with force and pressure in a fluid, because we actually need an equation of motion for this here. This is not enough. Good. So that's how we get into the question of force and pressure. And continuing here. I'll just refer to, I always draw a beaker. You know, you have some object in here, say a ball, and if it's the kind of thing that floats, you push down on it, it pushes back on you. So we have the buoyancy force. For instance. And we know that, this is just from experience, say this is the z-axis, then that in this beaker here, the pressure increases with depth, comma, because pressure increases with depth. And these types of problems are called hydrostatics. But when we get our dynamical equation, that'll of course be a very not necessarily trivial, but it'll be a subset of the dynamical equations. Okay, so let's look at the force on a volume element in the fluid. So this time we'll imagine we're in some large expanse of fluid and we're just asking about the force on some volume element. So I don't have to draw the beaker this time, but we'll just write force on a volume element. In the fluid, and then that force would be an integration of the pressure, and I'll write it down first. P d area, okay, and we'll just call this V for volume. Okay. And the reason for this minus sign is that the directed surface element is directed outward, just standard formalism, and therefore the force on the volume element due to the fluid is going to be opposite that direction. You know, well, we can do a little picture after all. So there's your volume element, and your forces are acting like that, but your D area is in the other direction. Okay, so what we can now do is also write P n hat D area. So there's explicitly the surface normal. And next, F in, say, the I direction is equal to this vector dotted into the xi hat. Let's write that. Into the xi hat unit vector direction. So that'll give us, from this vector, it'll give us this component, and that would be minus integral P xi hat dot n hat d area. And by the way, this was not a volume, this was the boundary of the volume, the surface that bounds the volume. Okay, we were using that formalism there. Okay. Is the ith component. And now we can use the divergence theorem again. This means that f sub I is equal to minus integral divergence of P x I hat d volume over that volume using the divergence theorem. Okay, so what is the divergence of this pressure times this unit vector, right? Divergence of a vector is a scalar, so that's what we need. And we need an identity from vector algebra that I'll have you guys prove just for practice. Here, let's go ahead and erase all of this. And when we use that identity, so I'm going to write down what we find first. Fi equals minus integral over that volume gradient of P d volume, because the divergence of a scalar times a vector. Should I write the general? Get the general formula here somewhere. Yeah, so P is a scalar, I'll put a vector A here. Okay. And that is gradient P dot A plus P div A. Okay. And when we apply this identity here, which really is just several lines, if you write it out, let's go ahead and call this homework, just so you've done it. And you could even just leave room in your notes to do it on the side. Okay, be that as it may, what do we have here? Divergence of a scalar times a vector, that's the gradient of the scalar dotted into the vector plus the scalar times the divergence of the vector. And so yeah, when we have what we're saying is we have P of our vector A of R, right, where the vector has 3 components and R is x, y, z. Yeah, back to this. So divergence PA or divergence P xi hat, so we have the gradient of P, fine, dotted into x hat plus P divergence. Now the divergence of x hat, that's just a constant vector, so that divergence vanishes, and that's why we have this right here. Okay. So and oh, one more step, because we said we have to dot it into xi hat dt, okay. And so that means we have fi is equal to minus integral over volume dp dxi d volume. Good, but then we can actually go back to the entire vector, and we see that we have minus the gradient d volume. So finally, we could say the force is equal to minus gradient p d volume over that volume. Good, let's enclose that in a different color here. Okay, so moving to this side of the board to complete this thought. So now we have the force, and now we're going to apply Newton's law. Okay. So Newton's law, we just write it down, mass times acceleration is equal to F, and that's clearly the net force, because we were, right, all the forces around on that little volume element. So if we go to an infinitesimal volume element, we've got the volume of fluid. Then what we have is rho dV dt, the force, is equal to minus the gradient of the pressure. Force per volume. So there's the mass per volume. So this is the force per volume. Basically, we just took our minus gradient P. dV was infinitesimal, right, over this infinitesimal volume element itself. So there's Newton's law, but it's not in the form that we can use it yet for a field theory, because we're actually thinking that this little infinitesimal drop is going to be pushed around somehow and move, as a semi-point mass, right, as a little particle. Not really a point mass, but right, as a little infinitesimal blob. Okay, so we have to do another step. We have to transform this derivative here to the derivatives as they appear in the field. In other words, we need not the motion of this thing, but the velocity vector at that particular point. So that's our next task. Say a couple of words about that, maybe. Okay, so far so good. So we've got mass per unit volume times acceleration. Let me give a little note on this before we move on. So before transforming it to a field, this minus gradient, imagine we have a positive x-axis, and the gradient is positive, 0, 1, 2, 3. Okay, we're in, some system of units. So if the gradient is positive, that means the pressure is greater at point 2 than it is at point 1. So if you have a little object here, if the gradient is positive, then the pressure is greater on the right side than it is on the left side. Okay, it is being pushed to the left. Okay, so the gradient is positive, but the acceleration is to the left. So I wonder if I could say that in so many words. Yeah. So I'll just write, if the pressure increases to the right, the gradient increases right, then force, or let's even write then net force to the left. Then net force to the left, and I'm referring specifically to this little sketch right here. And there's our infinitesimal piece of water. Good. Okay. So let's see here. We now have to transform that equation. So, here we go. So next, transform dv dt to the field expression. And we can do this as follows. We just imagine we're taking the time derivative of, let's just do this for Vx of x, y, z, and t. ddt Vx of x, y, z, and t. And the chain rule type of thing we always do, we would have dvx dx, and then dx dt, and all the way through. So we've been doing enough of that this semester. dy dt plus ddx dz dz dt. And then outside, where we would still have the explicit dvx dt. Okay. So you can see where this is headed. We're going to call this Vx, Vy, and Vz. And then we have a scalar product here between what we could call the gradient of Vx, dvx, dx, dy, dz, dotted into, well, the parentheses I got, gradient of dx dotted into the vector v. Or another way to look at this, or let's see if we can do this all at once. Or we could have v dot grad times v x. Because we'd have Vx ddx applied to Vx, okay. Then we'd have Vy ddy, so that's v dot grad applied to Vx, and we'd have Vz b dz applied to vx. So we can actually call this v dot grad vx, and in that case, since we started with vx, we have vx here, we end up with the following. d dt of the vector v in total is equal to v dot grad applied to the entire vector v, since we just had it for vx right here. So that is the important operation. And now we add, see, this was right here. So now we add plus partial v with respect to time. Okay, so this is an important operation. And what we can do now is incorporate this into this differential equation, and we have the result we were looking for. So yeah, leave yourself enough room to fiddle around with this. This is really an important operation, but we did it, right? We didn't leave anything out. Let's see where we want to put this. Send this up. And I'll take the right side here. Okay, so this results in, lock that off so we have everything. So we find dv dt partial plus v dot gradient is operator. V is equal to minus 1 over rho. We're going to bring the rho down to the other side. Gradient P. And that is Eulers' equation of fluid mechanics. What didn't Euler do? So that's Euler's equation. And we're just going to keep going through and setting up the equations so we get the complete set. Okay, so I'm not going to demonstrate anything about this thing just yet. I'll add that later. That's Euler's equation. One thing to notice is that this is a highly nonlinear expression here. Okay, it's not a linear differential equation. Even though you think, well, it could have been over here, right? But it definitely is not. Right, under circumstances it could have been, but here it is simply not a linear differential equation, and that makes it very difficult to solve. So Euler's equation and the Navier-Stokes equation that we won't derive, but I think I'll mention. In the full course we derive everything. Okay. But they're used in all manner of important applications where computers come into play. So if you're going into computational physics, you'll run into these equations, and having a fluid mechanics background where you derived everything, as a physicist, not a bad thing at all. Euler's equation. Okay. So I think I want to set all of the equations up before I do anything else. So we have this many. Let's see, we have continuity, we have Eulers. Yeah. Node, nonlinear. Source of all manner of interest. So now though, what do we have? We have V, P, and rho. That's 1, 2, 3, 4, 5 quantities. And we have 4 equations because this is 3 equations, a vector, and our continuity equation is 1 equation, scalar. So we need another equation, and we need a little bit of thermodynamics as well. dealing with ideal fluids. Ideal fluids. And in this case, that means no friction. No friction, no internal friction, and that means that there's no energy dissipation. Friction, so no energy dissipation. It's kind of like in mechanics where we do frictionless systems and we add friction in by hand often, or after we've treated the ideal system, we'll add some friction in. So we're in a similar situation here. No energy dissipation. This means that the entropy of this little particle of fluid, remains constant along its path. That entropy S, or entropy density in this case, S, I'll just call it S, remains constant. So this is enough to get another equation of motion, and then we'll set them all up and discuss it a bit. The entropy remains constant. ds dt equals 0. And again, we'll do this chain rule type of trick, but this one's a little simpler. So we have ds dt equals ddt s of x, y, z, and t, as with all of these quantities. And that will be let's do it. We could just read it off, but let's do it. So ds dx x dot, I'll do the short form, ds dy y dot ds dz z dot, kind of thing we've done before, plus partial s with respect to time. So yeah, that's going to be gradient s dot product with v again, the way we just had before. So what we end up with is ds dt from here plus gradient of s dotted into v. Maybe I rated v dot gradient s. Doesn't matter, but I'll show my notes here. Plus v dot gradient s equals 0. So that expresses that. And now I'll set up all of our equations. We don't actually use this one, but we don't use it explicitly, but we do use this property later on. So with all of these, I'm going to go ahead and set up the entire set of equations. I'll go ahead and erase this. You guys have it. And then I'll write down what we have now completely. So now we have equations of fluid mechanics, ideal fluid. So we already had the continuity equation, d rho dt, divergence rho v equals 0. So I'll call this equation 1. And we have the Eulers equation, dv dt, d dot grad applied to v equals minus 1 over rho gradient of P. And I'm going to put in here, because I got different colors, I'll use them. This can also be minus 1 over rho gradient P plus G. And G represents an outer field. Typically it's gravity, pointing down. But, so you can add this explicitly, but you don't have to, because this external field could be incorporated into the pressure such that the gradient, gives you G. So there's no problem there. One way or the other, so we've got that. And then we have what we just found, the SdP plus V dot gradient S equals 0. So we'll call that 3. Okay, that's complicated. But we can make sense of the whole thing. So what we have now, let's just count up all of our quantities. We have density, velocity, pressure, entropy. Okay, so that's 3, 4, 5, 6 quantities, and we have 3, 4, 5 equations, which is not enough. Not enough. Hold on a moment. Hey guys, keep it down or take it slow. Man, gotta yell at the guys outside. Oh well. It's all good. Here, where were we? So, that's 6 quantities, but only 5 equations. And this is where thermodynamics would come in, because you would always be able to link these equations via an equation of state. Okay, and that equation of state would be your extra quantity that's linking these. Okay, but rho P S will be linked by an equation of state. If you have to use them. The next thing I'll show you is that what we're dealing with, we don't have to use it. So that's how you get, that's how you deal with that. Good. So we're being thorough. Now, an important case is the incompressible fluid. Rho equals constant. It's an incompressible fluid. Incompressible or sufficiently incompressible to be called incompressible. Now in that case, we already solved. Then you have the divergence of V is equal to 0. So you've made use of this equation. Equation 1 gives us divergence of V is equal to 0. Rho's constant in here as well. And then you actually have enough quantities. So then equation 2, which is those 3 equations, and divergence of V equals 0, that gives us 4 equations for these 4 quantities, right? Rho's constant, so it drops out in that sense, for P and V. So I'll just write gives 4 equations for P and the vector V. How about that? Okay, let's see how we're doing time-wise. Man. All right, it takes time to be so thorough. We'll do a bit more. We'll do a bit more, but we have one more full lecture on this, and we'll get a couple of great applications. Definitely, we're not going to leave it hanging here, but I will continue with this, with just setting up the conditions for the whole thing, right? Those are equations. So we do have to say a little bit about boundary conditions. And I should point out, remember the first day I had these, last time I had this list of properties of the fluid, including that the forces were short range, okay? And we made use of those properties because using Gauss's theorem, the divergence theorem, kind of requires that to be consistent. So yeah, so these derivations are fairly principled. Let's just talk about boundary conditions, and we'll do some important applications next time. So boundary conditions. And they are that at a fixed boundary, or at a solid boundary, fixed boundary to a solid, V dot n hat is equal to 0, where that's the velocity field and that's the surface normal. What that means is, so here's our surface over which we have a flow. We'll use another color, so we got some kind of flow here, right? What that means is that the component that's in the direction of n hat vanishes at the boundary. Okay, and that seems kind of trivial. V sub z, or if that's the z-axis down, that V component vanishes, but the horizontal component does not vanish. So you can have some slip there. And that's required for these equations to be consistent. So yeah, that's what this expression means here. The velocity dotted into n hat, and n hat, after all, is the surface normal of this surface there. Now that condition that you can have some slip there, actually, let me see if I'm missing anything. I don't think I am. Yeah, fixed surface, V dot n hat. That's a compact way to write it. The thing is this, so, i.e., there is what we call it slip. We can have velocity moving along the surface. Now the important thing is that in reality that's not possible. Okay, so that leads to all manner of interesting things, and it takes the full equations, including a friction term, to have a consistent set of equations, consistent with physical reality. So that's actually unreal a bit. So let's note that this is for the ideal fluid. The real fluid has V equals 0 at the fixed surface. That's different, and that means that the perpendicular and the parallel components vanish. Yeah. So the real fluid And so the real fluid, and I'll just add to that, this requires the addition of some extra terms to Euler's equation. Nonetheless, there's a whole lot that can be done with this, as we'll see. But I'm going to leave that here. So here's what we're definitely going to do next time. We'll get through hydrostatics. We'll get through a couple examples of hydrostatics to make sure that we get Archimedes' principle. Okay, so pressure and depth and Archimedes' principle, we want to see how they arise essentially from the right side of this equation here. Okay, and maybe an application or two. And then if we could get to the rotating bucket, that's an interesting example as well. Okay, but that's where we are, and see you guys next time.